Well, now we're all just going to be really inappropriate, and everyone's going to know.
Uh-oh. So maybe I'll have to just send a link to Miss Coop if you're really inappropriate, right?
Actually, Ellen's not here, so.
Anyway, let's start. First, 4 things we're going to do. We're going to talk about something called the principle of superposition. Sounds really fancy. It's not. It's pretty much adding waves together and subtracting waves. That's all it is. Second, we're going to talk about constructive and destructive interference. And you've heard interference before, whether you realize it or not. Ever listen to the radio and suddenly there's static? That's called interference. It's a type of interference, but we'll go into what that is. Third, we're going to talk about how a wave can be reflected. And we quickly looked at that yesterday, where we looked at the animation of the rope, okay, where it was like on a pole, or it was on a hinge, or it was free in that window and it was flowing up and down. The fourth thing we're going to do is look at nodes and what are called antinodes on a standing wave. Okay, and a standing wave is a fancy way of something like a guitar string. When you pluck a guitar string, it sits there and it vibrates up and down, right? And you see this upper half of the wave and the lower half of the wave. That's a standing wave. Okay? So again, those are the 4 things we're going to do today. First, let's talk about. Okay? We need to define a lot today. There's going to be a lot of stuff we're going to define, so just make sure you're ready to write. Okay? Very little math in this section. Actually, there's no math involved at all. Okay? It's a lot of conceptual thought, and there's a good amount of understanding what terms mean. Okay? So for those of you that are usually used to the math, get used to the verbal part, and those that are having trouble with the math, maybe this is a nice little breather for math for once. Okay? So, interference. Interference is simply defined as 2 or more waves interact. Okay? So when 2 or more waves interact with one another, you get what's called interference.
What section is this?
12.4. This is the last section on your test. So your test is 12.1, 12.2, 12.3, 12.4. Okay? 12.1 and 12.2 is mainly where the math components come from. 12.3, there was a very small part of math yesterday with V equals omega lambda. And then today there's no math. So these questions you'll see mainly on part 1 and 2.
What's going on the test?
1, 2, 3, 4. Okay, 12.1, 12.2, 12. We'll talk more tomorrow. Can I make it easy? I think this will be one of your easier tests for sure. I'm honest, I'm not lying.
I looked at my friend's physics class. You're a teacher. And it was so much easier test than yours.
Anyway, superposition principle.
Well, I was trying to get my point across, but I kind of didn't say it right.
So superposition principle is the idea that 2 pulses, okay, 2 pulse displacements or 2 pulses can be added together when the 2 pulses exactly coincide. And we're going to look at these examples and these diagrams in a minute, okay? But again, when 2 pulses coincide, and coincide means when they meet one another. So if I sent a pulse down a rope and Hadley had the other end of the rope and she did the same thing, when those 2 waves met, something would happen. Okay, and that's what we're going to talk about now. They don't just it's not like they don't interact with each other. If there's a wave coming this way and a wave coming this way, something's going to happen between those 2 waves. Either they're going to add to each other or they're going to negate one another. And that's the 2 different things we're going to talk about here.
So constructive is when you it goes that way and then it comes back.
That's going to be reflection and inversion in the next section with the rope. Okay. This is if there were 2 waves sent together. So I'm going to explain it right here. Okay. Erica, question, go.
They'll meet and will they ever go together and form a bigger?
That's exactly right, and that's what this first part here is it right here.
Oh,
you're seeing that. We're going to go through this. Okay. So let's take a look here. I'm going to highlight what we're looking at. First, part A. Imagine this is me right here. Okay, not the dot, but I'm standing here. And I send a wave down the rope. And this is the wave that I send. And then Emmett's on this end of the rope, the same rope, and Emmett sends a wave down the rope. When these 2 ropes, or when these 2 waves come together, something is going to happen. Now, it's important to note that both of these waves are on top of the rope. Whereas in the next example, what do you see? One is below and one is above. Okay, over here, this one is above and this one is below.
When does that ever happen?
It actually does, and I'll go into a little more detail about that. Hold on. We're looking at an example that's simple with ropes first. So if these 2 waves come together, so this wave is moving this way, this one is moving this way. Let's go down to this section next. Okay? The 2 waves start to form, or they start to mesh together. Okay? This wave is coming from the left to the right, the bigger wave here, The smaller wave is coming in, and you see they start to mesh together. When they exactly coincide, okay, we can use the superposition principle. When they meet. And that's this right here. You see these little shadows right here? These little shadows? This is the shadow of the smaller wave right here. This is the shadow of the bigger wave right here. So when the smaller wave and the bigger wave meet together, they form an even bigger wave by adding the two together. So if the amplitude here was 3 and this was 5, this amplitude would be? Try again. This is 3. This is 5. 8. Okay? But focus, people. Everybody's like...
Seriously.
Okay? Steph.
I get the definition and stuff, but like conceptually, I don't get it. What are these things? When like, say, like we're screaming at each other, and like, those are the waves that they meet together.
Sure.
In the middle.
Sure, that could be one example of that. Waves can go way beyond sound. We could talk about electromagnetic waves interacting in this fashion also.
What's like the easiest example to get?
This is the rope, the idea of a wave on a rope. That's why I'm using it. Because if I start going into like, okay, well you look at radio waves, you look at like microwaves, you look at ultraviolet rays, like all these different things are going to have the same idea, okay, and there's interference. The radio waves in your car are a very easy example. Have you ever used what's called an I-trip? An FM transmitter? Okay. Alright, so imagine you go on a road trip. Before cars were able to dock iPods or able to just connect the auxiliary cable, who uses an iPod in their car? Hold on one second. Who uses an iPod? Okay, you just connect the cable, right? That's all you do. Because you have a newer car that has an auxiliary cable. So you just connect it. Before that, though,
You had the cassette, right?
well, there was a cassette, yes. And you can use that. What else did you use, though? That is right.
You have to like set it on. You push a button and it gives you like this channel.
The channel, and you had to.
Yes. That's called an FM transmitter. And what it used to do was this. You would put your iPod in this little dock, set the radio station to like 87.9, some station that doesn't come in. So there's no interference.
I know it.
Okay, it's an empty station. And it would transmit a signal to that station. Now, when I went on a road trip across the country, I was 20 years old, okay, when I was driving across country. And at that time, we used an FM transmitter. So we hooked it into the car, we found an empty station, we transmitted the signal. But what we noticed was when we got to like Ohio, suddenly that station came in Ohio. They had radio there. So our station, or what we were sending the signal to, wasn't working. And we're trying to figure out, why is this thing not working anymore? And when we turned it off, we realized, well, there's a signal coming into the car from the area that we're traveling in now, and that is interfering with the signal that we are sending. That's what's called destructive interference, where they're canceling each other out.
Wait, so why would you hear the other radio, not your?
Helping each other out?
Why would you hear both?
What happened was we would get both, a little bit at a time, but the signal coming from the people there was much stronger than the signal we were providing from a little FM transmitter, so it overpowered it. It'd be like a signal like this, and then this little signal. You wouldn't even hear the lower signal. Okay?
Oh, so you'd hear both of them. The worst
It would
is
be
when
like
you
in and
hear
out.
both
It'd
of
be
them
like,
what about when you hear the both of them at the same time?
Yeah.
That's the most annoying. Like,
That's kind of what it was.
When we drive to like Connecticut from Westchester, like there'll be ones that. What?
Nothing. I'm hearing noise. Go ahead, keep going.
I just made it.
Wait, no, drilling.
Yeah, like drilling. That.
I think it's the way. I think that's
All right. It is a vibration which creates a sound wave. That's right. Sorry, Erica. So yes, they interfere with each other. Sorry. Hey, real quick, let me pause and get maybe what we're getting at here is the idea. Here's the idea. Write this down. If two waves, no, just a statement at the end to summarize. If two waves have the same sign of amplitude, and I'll give a definition of what I'm saying. For example, here, these both have positive amplitudes, right? That's a positive, that's a positive. Whereas here, this was a positive and this is a negative down here. Okay, if they both have the same sign, you get constructive interference. So they could be both negative, by the way. Take a look. These could both be negative, and it would just be a bigger wave, but on the negative side. It's like adding negative and positive numbers, or only adding, like if you add two negatives, it becomes more negative.
Wait.
If you add two positives, it becomes more positive. These are both constructive interference. Destructive is when there's a positive and a negative, like this. Or a negative and a positive.
So
These are going to cancel each other out, whereas these are going to amplify one another. Okay? So again, I'll show you, watch, ready?
Should we say then constructive or... Oh, just kidding, because it could go out.
So take a look. Okay? If we go back to the original example, this was constructive now, over here. If they're both... I know it's upside down. If they're both negative, though, doesn't it just become more negative now? Okay? So it doesn't matter if they're both negative or they're both positive. All that matters is that if they're the same sign, it's constructive interference.
Wait, so you said how would you? Sorry.
No,
No, go ahead, Sibyl.
If two waves have the same sign of amplitude, then what?
Then it's constructive interference.
And
Okay.
destructive is when they cancel each other out.
When the signs are opposite, exactly. It's like negative and positive numbers. Think about amplitude above as positive and below as negative. Okay?
Yeah, but what if the amplitude on one side is larger than the other, regardless of like...
Well, then we have to figure out what can happen, and that's what we're going to talk
That
about.
one looks like that one's going to be smaller than the positive amplitude, so wouldn't that...
I agree. And take a
So
look.
does that mean that it would overcome it and make it go, make it all go to that one side rather than like...
That's what we're seeing in part C right here, and that's what we're going to talk about.
Oh, okay, I get it.
So we get,
That makes
make believe this wave has an amplitude of 8. Okay, look up please. Make believe this wave has an amplitude of 8.
sense.
This one may be like negative 3. 8 and negative 3 gives you 5, right?
Oh,
So that means the resultant wave is 5.
Okay.
But one thing you should write down at the bottom is this. After they interfere, they continue as if they were normally the same waves. Take a look at part D of both of these
They
cases.
coincide, they're with one another now.
Well, they overlap and then they pass through each other. So the original waves still exist.
Oh, so they go like this, they meet, and
And then they keep going the way they had started.
I don't get that.
So look at part D here, okay? See how this wave was big and this wave was small right here, Steph? They coincided and they canceled to get this wave, but afterward, what happens? This wave here continues on its way through. This wave on the bottom still continues, but it's passed. So they pass through each other. Waves are not matter, okay? Waves pass through one another the same way they had started.
But
Okay?
then how can you say that amplitude has like 5 now from 8 and negative 3?
Because when they're together, they cancel each other out, but once they pass through each other, they're separate again.
Oh, but those are
It's the same waves as you had, yeah.
Those are but they're going
So
the
this,
opposite ways.
so ready, let's go through this. Ready? Let's put numbers to make it easy.
There's a 5 wave going to the left and a 5 wave going to the right.
No. This is the same waves they started with. Look. So if this was an amplitude of 8 and that was negative 3, that would yield 5, right? What happens is it continues with 8 and negative 3. It's the same waves they had. Now they just pass through each other. So all that's going on here is you're sending a wave down the rope this way, another wave this way. They meet and combine. Either they get bigger for constructive or they cancel each other out for destructive. But then what happens is those first waves you sent, they combine, but then they pass through each other.
So
And they continue the way they started.
They keep that same number?
Exactly.
So
Absolutely.
only at the time they meet, they're 5.
Yes.
Then after...
When they meet, they interfere,
It's
but
going
afterward they're the same. Exactly. Yep.
Wait, but then do they switch the signs
Nope,
when one
nope,
becomes
nope.
negative? Oh.
Nothing changes. They just pass through each other. But for that instant in time, when they pass through each other, they combine to become 5. And then they continue passing through each other. This 8 that was over here passes through the 3, and this 3 continues left, the 8 continues right. It's like, give me 2 demos. Hadley and Snow, come on, real quick. Okay, it's going to sound kind of weird. You're taller than she is, right? So, if you guys were to walk together toward each other, and somehow you were able to stand on each other's shoulders, okay? What's your height approximately?
5, 7.
Okay, 5.5 feet. 5'2". So let's say 5.5 and 5. I know you're not. Okay? 5.5 and 5.
I'm 5.
Together, they would make 10.5, right? So at this instant in time, it'd be like they're standing on each other's shoulders. But what would happen is, they would then pass through each other, so walk around. and they would continue with the same magnitude they started with. So even though she started with 5, and she started with 5.5, and they combined to be 10.5, they then continue the way they started.
And so then she would be 5.5, and she would be 5.
She's still 5, she's still 5.5, and they just pass through one another. Okay? Thank you.
No problem.
Does that make sense, Tristan? So they're combining for that instant in time, and then they just continue the way they were. It'll give you a wave this way and a wave this way. It'll maybe give you an amplitude and say, like, one wave has an amplitude of 7, another has an amplitude of -3. When they combine with one another, what is the resulting wave? Well, it's just 4, because 7 would be here. 7 and -3 would give you just a 4 in the middle, and then they would continue to pass through each other. Okay? Here's another example. Okay? Well, you know what? I'll wait till tomorrow during the review to give that example. Let's go to the next thing. It's continuing with what we talked about yesterday real quick. Okay, with a pulse.
Is this going to be on the test?
Yes, again, this whole section is on the test, guys.
Oh, wait, I have another question real quick about it.
Go ahead, Steph.
Does velocity matter, like in terms of displacement, if one wave is going to the left or the right? Does that have to do with amplitude, like being negative?
Well, they have to meet, so they have to be going in opposite directions.
Okay.
So if they're not, like if they're both traveling like this way, but they're separated by a gap, they're never going to meet, so there's never going to be any interference.
True.
Unless this one catches up to this one or something.
Would we ever have to do something?
You're going to only have where they're meeting together, going like this. Okay? So, this is a good example now with the slinky. When I was sending a wave to Nicole, the wave that would return would be the negative of that wave. Did you notice? Did anybody see that or no?
Absolutely no.
Write it down and we'll show it quick again, just to show it real quick.
What are we looking for?
Watch the wave that I send is going to be on top of the slinky. You're going to see like a positive amplitude, and then the wave that's going to come back from Nicole automatically is going to be a negative amplitude.
So yours is going to go like that, and hers is going to go
underneath.
Like this.
Okay, so just watch carefully. There's the top, and then hers comes down below. Top, bottom. Can you actually notice that or not?
Yeah, no,
Be
you
honest.
can. Do a bigger one.
Okay, let's make a bigger one. Dampen.
Damn.
Okay. You want to go? Go ahead. Send a pulse to me. Okay. A little higher, a little more of a pulse. There you go. Okay. Top, bottom. So every wave that's returning from me is on the bottom. Every wave she was sending was on the top. If we both did this, we're going to get some weird looking things going on. This is called a standing wave. Keep going at the motion you're going at. Okay? What you're noticing is that you're seeing this fluctuation. It looks like 3 different waves together, and there's what's called a node right here. There's not much of a change right there, if you notice.
Yeah.
That's kind of staying stationary. Does everybody see this right here?
Yeah.
See how that's stationary? And the waves are just going up and down?
See it?
That's the next thing we're going to look at, which is called a standing wave. But for this right now, dampen. Okay, for this, I'm going to send one to you. All I'm doing, good, is going to send one wave and watch the wave that she returns. You see how it's coming on the bottom now when it returns? It's because it's inverted. That's the example right here. See fixed boundary? When you send a wave to a fixed boundary, meaning her hands, they're stationary, they're fixed. The wave goes on the top, but then look what happens. The wave it sends back is reflected, and it's on the bottom. It's sending the negative amplitude back. But if you were to send a wave to something that could move or slide, the rope is going to slide up, and then this rope is going to fall back down, sending the exact same wave back. So when the end is free, the same wave goes back. It's identical. But when the end is fixed, it's the same wave, but it's on the negative side. It's on the negative side. Okay? Erica.
Have you ever played what's a game where like you have to throw the tennis ball against the wall and then like you have to watch it?
Handball.
Handball.
It's not tennis ball, but yeah.
Well,
tennis ball.
I guess you didn't have to use that, but like you know how you throw a ball and then like the minute that it hits it goes straight to the ground. Can you think of it like that?
The minute it goes straight to the ground?
The minute it hits the wall, instead of coming like straight back, it goes down to the wall. It like immediately starts to go down to hit the floor first. Like a wave, you know how a wave it hits the wall and then it goes down?
Sure, but that's just gravity. But if you want to think of it analogously, that makes sense, I guess. Yeah. It's not a wave though. That's why I don't want you to think that way.
That has to do with the.
No, I get it has to do with gravity, but I'm talking about the motion of
No,
it.
that actually has to do with the theta.
Theta.
Theta like
Remember, I said theta by accident. I told you the whole story.
Is it still recording?
Yeah.
You don't remember
All right.
that was theta for like
Feta.
Erica, I understand what you're saying. If that helps you, that's fine.
Okay.
Okay? Again, what you need to know is that a free end sends the same exact pulse back, whereas a fixed end sends the negative pulse back. Okay? This is going to lead us into, which is called standing waves. Okay, which is called standing waves. So a standing wave is a wave pattern that results when two waves of the same frequency, wavelength, and amplitude travel in opposite directions. There was a point in time there when Nicole and I were both oscillating the ends of our springs with the same exact motion. That's what caused that stationary point to exist in the middle. And that's what caused the wave to look like it was the same wave and just fluctuating up and down. Okay? Just fluctuating up and down.
What's the definition of the W again?
Omega?
Yeah, what is
Frequency.
Yeah, but what is that?
Did you hear that, Andre?
The time,
No, tau is time.
no, the amount of times
I heard it.
that it completes a cycle in a given period.
He's gonna drop a lot of bombs.
No, he didn't drop a lot of them, but he dropped the today, and I was like, what?
Who did?
Enough.
We're being recorded, guys. Stop gossiping about faculty.
Now, a node is a point in a standing wave that undergoes complete destructive interference. That was this point right here that I was pointing out that wasn't moving. You kept seeing the wave bouncing up and down, but there was like this point that wasn't moving at all. That's called a node. Okay? And I'm going to give you an image of this in a second, so just write it down for now. Okay? It will help with an image, I promise. What you should know, though, is complete destructive interference, what that means. This, complete destructive interference, is when two waves exactly are opposites and they cancel.
No.
So like this. If this wave was -4 amplitude and this was 4, what would they become when they came together? Marcos? 0. Good. You got the 4 and the -4, they cancel, right? So when these two waves coincide, you have no wave that exists. That's what that node is. That stationary point, when me and Nicole were oscillating the spring up and down, that stationary part was a node. Okay? And what a node looks like, when you see a standing wave, that's what a standing wave looks like, and we'll show an image in a minute. Those are the nodes. And you're going to see this wave oscillating up and down. And that's probably what some of you on the side, like where Caroline and Hunter are, you probably saw that. You saw like these little waves moving up and down like that. And those dots there, those are the nodes. The antinodes are simply the crest and the trough, the tops and the bottoms, the mins and the maxes. It's the distance halfway between the nodes. Okay, so these are the antinodes right here. And I'll highlight them on this image.
Are those the ones that move with the wave?
Correct. Those are the parts of the waves that undergo complete constructive interference, or just constructive interference. It's when the amplitudes are occurring with one another, that they amplify each other. The red hash marks are the nodes there.
Aren't nodes
The antinodes, sorry. The green dots are the nodes. Erica.
Oh, I'm thinking of nodules.
Thinking of what?
Nodule, like a node.
No, like Nigel Thornberry.
Nodule.
I know.
You don't know what a nodule is?
No, what is it?
It's
Define
like,
it.
it's like something that like sticks out, or like, isn't it? Like a
I
throat
don't know.
nodule. Like, have you ever heard of a throat nodule? Like when
No.
someone has like
You
something
definitely
on
got
their-
your nodules taken now, Mr.
No, it's not. It's something that you develop. It's like singers get nodules. I thought you would know what I was talking about, so I'd be able to write.
That's the example.
Who drew that
So which
train?
one is the antinode? The X
Who drew that?
The X's are the antinodes. That's what I was going to show you in the next diagram.
I'm sorry.
Again, the X's are the antinodes, the green dots are the nodes.
Who drew that train?
I have no idea.
I did.
Oh, Lova did.
Who?
Lova?
Novocaine?
I didn't know
Lovacaine.
that. Lovacaine?
It's like a rap name.
No, it's like Novocaine.
Where is Lova today?
She's sick.
She's sick.
She's on,
She's here
Here
yesterday.
she is.
the
Hadley.
section.
Gosh, Hadley.
That's so
Mean.
rude.
I love how it's recorded.
Yeah.
She's
Lova's listening at home right now. Lova, we all miss you, Lova. We feel bad that Hadley didn't know you weren't here today. Well, she heard you already. Hadley will apologize to her tomorrow when she's here.
Erica doesn't know this week.
I'm just giving you a hard time. But for real, she was gonna watch some video.
For real, yo. On that.
All right, let's go. Let's go to the next part, please.
Those look like almonds.
Now, you don't have to draw this, please. Just look up for now. If you want to sketch it, you can. So, first, please listen. Let's identify the nodes. So when there's a standing wave like a guitar string, that's the first example at the top. The nodes are simply the ends where the guitar is fixed. Now, imagine for those guitar players in the room, you know what a capo is we talked about? A capo? The thing you clip on to make the frequency higher. Okay, imagine there's a capo put on right here. That creates another stationary point. So this would be an example where there's a capo in the middle of the guitar string now. So when you pluck on the left side, only this side might be vibrating up and down. This one would probably stay flat. Okay? You're plucking on the right side here. Now, on the next example, this is just examples of more different, types of waves. Here there would be 4 nodes. Here there would be 5 nodes. Now, let's identify the antinodes. It's simply the max and the mins. Those are the antinodes.
This is like chromosomes. Wait, this is biology, you know?
Yeah, DNA.
Yeah. And then like the.
Wait, this looks like mitosis.
It does look like
It is
DNA.
telekinesis.
Yes, that's what I was going for.
Okay? Now, here's what you should notice. The antinodes come in pairs. So this is like one antinode. This is another antinode. This is another antinode. Okay? So the node at the bottom you'll see is there's always going to be one more node than antinode for any given standing wave. And make sense of it, please. And look at the bottom example. You have 5 nodes. 1, 2, 3, 4, 5. You have 1, 2, 3, 4 antinodes. Okay? There's always going to be one more node than antinode. Emmett.
Wait, where's the 5th one?
So 1, 2, 3, 4, 5. Okay? And then there's 4 midpoints because there's 5 segments in a sense, or 5 endpoints.
That's going to be one of the multiple choice.
Isn't each crest and trough,
It represents one antinode, yes.
So isn't there 8 there?
No, together they're 1, I'm saying. Because remember, this wave is the same, this is the same wave fluctuating up and down. So it's a crest at some points, but then it's a trough, and then it's a crest, and then it's a trough. Let's look at this example on the right to really identify that, or really emphasize that. This here, okay, is the same as this right here. It's just over time it's fluctuating up and down. This is fluctuating up and down, and it becomes this. When you put these two waves together, you get something like this. Okay, which is what we've been looking at the whole time.
Is that like an algebra, like when you're graphing something, degree, like when you're taking the degree to find out the max turns, so it's one less?
Sure. Yeah, you can name it that way, absolutely. Yep. I'll put the homework on Moodle. It's already up there. Finish your lab tonight. Problem said due Thursday. Tomorrow's review. Make sure you have your questions ready for tomorrow.
For the labs, would it be .31?